part of Modern Machine Learning Technology and Data Science Conference 2023. And now I am excited to share with you a presentation to the article on the topic Product Recommendation System using Graph Neural Network by Yuliana, Lavryk and Yurii Kryvenchuk. So, throughout this presentation, we will explore the fundamental principles behind graph neural networks, their applications in recommendation systems, and the transformative impact they have on enhancing customer experiences. Now, let's dive into the world of graph neural networks and uncover their remarkable potential. So, what is GNN in general? GNN, short for Graph Neural Network, is a cutting-edge machine learning framework specifically designed to process and analyze graph structure data. By leveraging the inherent relationships and connections within a graph, GNNs enable us to capture complex patterns, extract valuable insights, and to make accurate predictions. This revolutionary approach incorporates both node and edge features, allowing us to understand and model the intricate dependencies between entities. So let's look at the diagram which describes the graph network in the terms of recommendation systems. This slide shows main steps of using GNN for recommendation system. Let's go through. The first one, get graph representation. It means that the first step in utilizing GNN for recommendation systems is to construct an appropriate graph representation. This involves mapping the relevant entities such as users, items, and their relationships onto a graph structure. Each entity becomes a node, and the relationships between them becomes edges, forming a rich, interconnected network. The second one, learn node embedding. Once the graph representation is established, GNNs learn node embeddings, which capture the latent features and characteristics of each entity. Through an iterative process, GNNs update the node embeddings by aggregating information from neighboring nodes, effectively encoding contextual information into the embeddings. The third one, aggregation. So, in the aggregation step, GNNs gather and propagate information across the graph structure. This process involves aggregating the features and embeddings of neighboring nodes, capturing the influencing relationships within the graph. By iteratively updating and refining the node embeddings, GNNs generate a more comprehensive understanding of the graph and its entities. The last two ones, main ones, make predictions and get recommendations. So, with the enriched node embeddings, GNNs can make predictions for recommendation tasks. By leveraging the learned representations, GNNs can estimate a user's interest or preference for specific items. These predictions are typically based on user-item interactions, historical data, and the graph structure itself, allowing for more accurate and personalized recommendations as well. And the last one, final, get recommendations. Finally, GNNs utilize the predictions to generate recommendations for users. These recommendations can be ranked based on the estimated preferences or tailored to specific user preferences, providing personalized suggestions that align with the user's interests and needs. GNNs excel at capturing deep relationships and dependencies in the graph. So, by following the steps, GNNs enhance the recommendation process using power of graph structures, contextual information, and user-item relationships, resulting in more effective and personalized recommendations for user. Now, let's move on to the advantages of using GNN for recommendation systems. So, among the numerous advantages of GNN networks, the following can be highlighted. The first one, modeling complex relationships. So, this one is which has already been partially mentioned. One of the key advantages of graph neural networks in recommendation systems is their ability to effectively model complex relationships. By considering the connections and interactions between entities, GNNs can capture higher-order relationships, uncover latent patterns, and provide more accurate recommendations. The second one, capturing heterogeneous information. GNNs have the capability to handle heterogeneous information within the recommendation system. In addition to user-item interactions, GNNs can incorporate diverse attributes and features associated with users and items. This allows GNNs to capture and leverage rich and varied information such as user demographics, item metadata, and contextual information. Also, flexibility and adaptability. GNNs offer flexibility and adaptability in the recommendation process. They can handle different types of recommendation tasks, including personalized recommendations, item to item recommendations, and even group recommendations. And the last one, addressing cold start problem. The cold start problem, where there is limited or no user or item data available, is a common challenge in recommendation systems. GNNs have shown promise in addressing this problem by leveraging the graph structure and incorporating information from similar users or items. So, GNNs can provide reasonable recommendations even for new users or items by inferring their preferences based on the connections and similarities within the graph. So, now we can move on to the particular research conducted and described in the presented article. First of all, selected data for recommendation system based on GNN. So, the research described in this article used Amazon product metadata and Azamar customer reviews dataset, namely data related to the category books. Before building the model, these datasets are combined into one based on the Amazon standard identification numbers. And now, briefly about these two types of data. So, Amazon customer reviews includes product reviews and rating by users. It can be used to construct a bipartite graph that connects users and products based on their review history. And Amazon product metadata refers to the structured information associated with products available on the Amazon marketplace. After downloading these datasets, they were merged and then sampling was performed. Namely, there were selected users with more than 10 transactions from merged dataset to analyze users with really sufficient user history. Now we can talk about model architecture used in this research. So, there were researched different types of GNN models architecture, and the graph sage was selected. Graph sage architecture is used because such an approach can overcome large graph problem and is useful for graphs that have large amount of node attribute information. Let's take a closer look at this architecture. So, this slide describes the main parts of the GNN architecture named graph sage. First of all, the model must receive input data in the graph representation. Then the model contains GNN encoder. This class represents the GNN encoder module and consists of two sage convolution layers. These layers perform node replacement and aggregation in the graph. So after that, one more important and significant part, transformation reviews with metadata in the heterogeneous graph. The GNN encoder instance is then transformed into a heterogeneous graph using the special function, which takes into account the metadata and specifies the aggregation method. And the last one, edge decoder. This class represents the decoder module which processes the graph edges to predict internode relationships and consists of two linear layers. Finally, the result is passed through the second linear layer, and the output is reshaped to one-dimensional tensor. So overall, the model takes node features and edge indices as input, performs node-wise encoding using graph sage encoder, and decodes the relationships between nodes using the edge decoder. As a result, we get predictions which are the predicted rates, and top-curated books will be considered as recommended books. So, and the last thing that is important to talk about is the evaluation of the built model and the results of tuning it. So, there are several metrics used to evaluate the performance of recommendation systems. Let's go through. The first one, which was used during training process as last function, is RMCE, which is root mean square error. So this metric defines whether the rating predicted by the recommendation system are close to the actual ones. The second one, precision, measures the proportion of relevant recommendations among the total recommended items. And the last one, recall, it measures the proportion of relevant items that have been successfully recommended among all the relevant items. This matrix can help identify the strengths and limitations of GNN-based recommendation systems and guide further improvements in the model architecture. So, these matrices are used in this research and the results are described in the table on this slide. So, you can see that they conducted experiments with different optimizers and learning rates to tune the model. And based on the results in table, there is a conclusion that the best performance has a model with the optimizer Adam learning rate 0.01, when precision and recall are highest, and RMC value both for train and validation or test samples are slightly above 1, which means that the build predictive model appears to be performing significantly well at predicting users' rating and giving relevant recommendation. So I guess that's all from my side, and I thank you